first let's talk about the variation theorem. The idea behind the variation theorem is if you guess what the wave function is, okay, and you try to make your wave function adjustable, you introduce adjustable parameters to it so you can tweak it, and you can use it to estimate the energy. The idea is, regardless of what you do, as long as your wave function, your trial function, your guess, follows the same or obeys the same boundary conditions as the correct wave functions, you will always get an energy. The energy that you calculate, the estimated energy you calculate, will always be higher than the lowest possible energy. So the variation method is used if you're interested in looking in the ground state energy or the lowest possible energy of your system. Okay? So the theorem says that if you have a trial function phi and it obeys the same boundary conditions as the correct functions, which are psi, okay? So these are the correct wave functions, and this is your guess. Okay? If you calculate this integral right here, so phi h hat phi in bracket notation divided by phi phi in bracket notation, that will always be larger than, greater than or equal to the ground state energy. Okay? The lowest it can be is the ground state energy. So if it's possible for your phi, the way you write your phi is you introduce things there that you can adjust. If it's possible to adjust your phi so that it will exactly look like the correct ground state wave function, then you'll get the ground state energy. So that gives you some kind of a goal, a strategy, so to speak, to find the energy of the ground state energy of your system. Okay? And so let's prove that. So if phi obeys the same boundary conditions as your psi, then you can write, that should be phi. Remember we said we're postulating that eigenfunctions of a Hermitian operator for physical properties form a complete set, right? So we should be able to write phi as a linear combination of the correct psi's, whatever those are, right? So you can say phi is equal to C1 psi 1 plus C2 psi 2 plus and so on and so forth, right? So if we use all the possible psi's, we can take a linear combination and get the correct expression for phi. Right? So what would your phi h hat phi in bracket notation be equal to? Let's write this in integral form. This is going to be what? Okay, it's going to be phi star h hat phi d tau, where d tau is integration over all possible space, right? So that's going to be equal to C1 psi 1 plus C2 psi 2 plus and so on and so forth star h hat C1 psi 1 plus C2 psi 2 plus and so on and so forth integral over all space, right? So all I did here was substitute for phi. This is my phi star, and this is my phi. So what do we get now? We've seen this before. Since your psi form an orthonormal set, what are the only terms that will survive? Like terms, right? So like if you did C1 psi 1 star h hat C1 psi 1 d tau, so that would be between this one and that one, right? So let's expand that, and then let's do this one and this one. What would that be? Integral of C1 psi 1 star h hat C2 psi 2 d tau, And you're going to have two more terms, right? More terms. Let's examine this term right here. What's h hat C1 psi 1? H hat is a linear operator. I can factor out my C1, right? And C1 star, I can also pull that out of my integral, right? So that's going to be C1 squared. So this part right here is C1 squared. What's left inside the integral? Psi 1 star h hat psi 1 d tau. But what is h hat psi 1? Psi is an eigenfunction of the Hamiltonian, so that's going to be E1 times psi 1. So I can factor out my E1. So this becomes, I can rewrite this as C1 squared times E1 integral of psi 1 star psi 1 d tau. And what's integral of psi 1 star psi 1 d tau? 1. It's normalized. So this thing is 1. So this term just becomes C1 squared E1, right? Well, what happens if you did this part right here? You're going to end up with what? An integral of psi 1 star psi 2 d tau, which will make it 0. Okay? Psi 1 star and psi 2 would be orthogonal. So this term is going to drop out. So the only terms that will survive will be, so you end up with C1 squared E1 plus C2 squared E2 plus, and so on and so forth. Okay, or we can write that as the sum of C sub I squared E sub I. So that's your numerator. What about your denominator? This is going to be C1 psi 1 plus C2 psi 2 and so on. And then you have C1 psi 1 plus C2 psi 2 plus and so on. That should just be equal to what? Sum of C sub I squared. Right? So let's take the ratio. So sum of C sub I squared E sub I divided by sum of C sub I squared. Okay. Is that greater than or equal to E1? That's what we're trying to prove. Variation theorem says that this expression right here on the left must be greater than or equal to E1, where E1 is the lowest possible energy. So E1 is going to be less than or equal to E2, less than or equal to E3. So E1 is the lowest possible energy. Right? Is that true then? Well, let's just take the simple case where we just have two terms. Okay, so you're going to have what? C1 squared E1 plus C2 squared E2. Is that greater than or equal to summation of C sub I squared times E1? Well, let's see. Let's look at this one. This is just going to be C1 squared plus C2 squared times E1, right? So this one becomes what? C1 squared E1 plus C2 squared E1 plus, and so on and so forth. And this one you have C1 squared E1 plus C2 squared E2 plus, and so on and so forth. What do you notice? C1 squared E1 cancels out, right? Is this left-hand side equal to the right-hand side? I mean, greater than the right-hand side. Okay. C2 squared E2, is that greater than or equal to, okay, that should be plus more terms, right? Plus C3 squared E3, would that be greater than or equal to C2 squared E1 plus C3 squared E3, okay, and plus extra terms. E1, sorry, this should be E1. Is that true? What would make that true? Then E2 must be greater than or equal to E1, and E3 must be greater than or equal to E1. But that's what we're saying to begin with, right? E1 is the lowest possible energy. So this left-hand side must be greater than the right-hand side. So that's the proof for the variation theorem. So you can take advantage of that to get an approximation for your lowest possible energy.